Hey everyone, welcome back to the series. So far we have seen Greedy fail on coin change and then triumph on activity selection. Today we go even deeper. We will see Huffman encoding, which is a greedy algorithm that solves a real-world problem you interact with every day, which is data compression. The core idea is simple. In standard text encoding like ASCII, every character takes exactly 8 bits. So, whether it's a rare letter like Z or a super common one like E, no matter of their frequencies, we are using the 8 bits encoding for all of them. But what is the problem here? Let's say Z is used 3 times and E is used 100 times, let's say. Then the average bits per character is 824 divided by 103, which gives us 8 bits, as we expected, of course. Because no matter what is the frequency, we are always using 8 bits for each character. However, that is so wasteful. And as you can see, Dino is not accepting that, of course. She is saying that why the heck did you give all of those bits unnecessarily? And she's right. And she says that from an information theory perspective, this is inefficient. Since E appears much more frequently, we would like to represent it with fewer bits. At the same time, we need to allow rare characters like Z to use more bits. For example, if we used 2 bits for E and let's say 8 bits for Z, we would get 224 divided by 103, which is nearly 2.17 bits per character in average, which is much more lesser than 8 bits. So the idea behind Huffman encoding is that it assigns shorter bit codes to frequent characters like E and longer codes to rare ones, as we saw in the case of Z. By doing that, it minimizes the total bits needed to represent a message. Let's see where is it used in a real-world situation. Huffman coding is a core component of the deflate algorithm used in zip files. After repeated patterns are identified in the file using a specific compression, Huffman coding assigns shorter bit sequences to more frequent symbols. It is further reducing the file size. So it's used for additional compression, we can say. Also, Huffman coding is used in the final encoding stage of every JPEG image. After image data is transformed, the resulting coefficients are encoded using Huffman code so that frequently occurring values require fewer bits. In MP3 audio compression, it compresses the frequency domain data produced during audio encoding. Common frequency coefficients are represented with shorter codes, which is of course helping reduce the storage required while preserving the audio quality. So every time you send an email, load a web page, or share a picture, Huffman encoding is quietly working in the background to make those files smaller and faster to transfer. Let's try to understand what we need in order to use this algorithm. First, we need the information of how many times each character appears in the input text. For example, if you are implementing the algorithm in Python, you can use dictionary here. Then we need the main flavor, which is the binary tree. It's going to hold our characters in its leaf, and at the end of the day, we will assign codes by traversing the tree from the root to the desired character. And the code length will be determined by the depth of a character's leaf node in the tree. We will see that in our example. Also, another important flavor is the priority queue. Actually, this is the main key data structure that we will use to get the lowest frequency characters first while we are constructing the tree. And the goal is to minimize the summation of frequency multiplied by code length for all characters. So yes, these are the main recipes for the Huffman encoding. We will understand them better when we see an example in a minute. And here is the algorithm. For now, I will just read it. As I said, we will understand it much better when we solve an actual example step by step. First, we are counting the frequency of each character. As I said before, we can use dictionary, for example, for that purpose. Then, we insert all characters into a min priority queue sorted by frequency. Why? Because we want to reach the characters which have the lowest frequency first when we build the tree. While the queue has more than one node, we are doing the following tree step repeatedly. First, extract the two nodes with lowest frequency. Then we create a new internal node with the summed frequency of these left and right nodes. Then we insert the new node, the parent node, back into the queue. And at the end, when there is only one node in the tree, it is the root of the Huffman tree, which means that the while loop is completed. And at the end of the day, in order to assign codes, we read each character's code by tracing root to leaf path. And while doing that, if we go left, we write 0. If we go right, we write 1 in the code. Let's solve an example to see how it works. This is our problem. We have this string, which has 15 characters in total, and the goal is to find the Huffman code for each character and the total bits needed to encode the string. First, we need to count how many times each character appears in the string. Here is our string. We have 3A, 5B, 4C, 2D, and 1E in our input string. And the total number of characters is 15. As we said before, if we use ASCII encoding, we would give 8 bits for each characters. So that means that this would take 15 multiplied by 8, which results in 120 bits. Let's see how much Huffman can compress this. After I created my dictionary containing the frequencies of all characters, I insert all characters sorted by frequency in my priority queue in a way that the lowest one is going to be the first one. Then I start picking the first two items in my queue. In this case, we have E and D. Afterward, we are combining these two nodes to create one internal node called ED as a parent node of these two, which has the sum frequency of these two nodes. In this case, it's going to be 3. Then I insert this new node ED inside my priority queue. Since ED has frequency of 3, it's going to be at the front of the queue again. I continue iterating and taking the two lowest frequencies as long as there are at least two nodes still available in my queue. At this time, ED and A have the lowest frequencies, as we can see. I combine them and create a new parent node called EDA. And again, I am putting this new parent node EDA, back into the priority queue. However, since EDA has a frequency of 6, since we summed the frequency of these two nodes, it's going to be at the end of the queue now. Now, the next two nodes are C and B. I'm combining them and creating a parent node called CB, which has the summed frequency again. And again, I am putting it back to the queue. As you can see, however, since C and B is not related with EDA yet, they are separate trees for now. Now, we have EDA and CB as our next two nodes to be combined. I combine them, add up their frequencies, and assign it to the new parent node. And we can see that these two nodes are the last nodes in my queue. So this new parent node will be the root node of my tree. That means that our tree is completed. So now we can reach the code of each character by traversing the path from the root node to that character leaf node. As you remember, initially we said that whenever we go left, we will write 0, and whenever we go right, we will write 1. Now let's find out the code for each character. We will always start from the root and try to go to the leaf of that character. For E, I am starting from my root node and ask which way should I go to reach the node E. In the root node, I ask which way should I go. As you can see, EDA is on left. So I am going on left and I am writing 0 in my code. I am asking which way should I go? It's on the left. So I am again writing 0. E is on the left side of ED. So again I am going to left and writing 0. What about D? Again I am starting from the root node. We need to go left. We need to go left afterwards. And at the node of ED, I need to go right in order to reach the node of D. So which means that the code for D is going to be 001. For the character A, I'm starting from root, going left and going right. So the code for A is going to be 01. For the character C, I'm going to write because CB is on the right. Then I'm going to go to left in order to reach C. So the code for C is going to be 10. And finally, the code for character B is going to be 11 because as you can see, from the root node I need to go right and from CB I need to go right again in order to reach B. So at the end we can say that E and D have 3 bits and A, C and B have 2 bits. So if I calculate the total bits used in this input, it's going to be 33 bits. And from that, we can calculate the average bit per character by dividing this by the total number of characters in our input. So 33 divided by 15 is going to give us 2.2 bits in average. As you remember, if we used ASCII, it would be 8 bits in average. So we can directly see that we saved a lot of space by using Huffman encoding. Now that we have covered Huffman encoding, let's see how all the greedy problems in our series compare in the judgeboard of the week. We saw that we can't use greedy for 1 or 0 knapsack because items cannot be split, results in a locally best item preventing a better overall combination. So we need to use dynamic programming for that. In the same way, we saw that coin change is not suitable for greedy approach since local best does not mean the global best. But for fractional knapsack, activity selection and Huffman encoding, we can use greedy because making the global optimum choice never prevents reaching the global optimum in those problems. So overall, we can say that Huffman encoding assigns shorter codes to frequent characters and longer codes to rare ones, minimizing total bits. The algorithm is greedy, which states that always merge the 2 lowest frequency nodes in the queue. We have seen how we are solving a problem by Huffman encoding step by step. We talked about the algorithm and the required data structures to solve that. And we also saw that real compression formats such as zip, JPEG, and MP3 all use Huffman coding as a core building block. So, Huffman encoding is where the theory meets practice. Actually, it's one of the most elegant examples in computer science of a simple greedy rule producing an optimal real-world result. Next, we will see the longest common subsequence. And in this one, we go back to dynamic programming again. It's used in DNA analysis, diff tools, and version control systems like Git. It's also quite interesting and very common problem being asked in interviews. I hope you liked this video. If this helped, please hit like and subscribe. Thank you for watching and see you in the next one.